Welcome again to the new lecture of this course, Solar Photovoltaics Principles, Technologies and Materials. So, we will just recap the last topic that we started. So, in the last lecture we started discussion on p-n junction, and this is basically p-n junction in dark without any light illumination. P-n junction is essentially a junction between two semiconductors, one n type and one p type typically, and generally we look at it in the context of identical homojunction, that is n silicon on one side and p silicon on other side, and as you put them together, so you have n silicon and p silicon making a junction, and as you put them together, the Fermi levels of these two semiconductors align with each other, because Fermi level has to be same throughout the device at equilibrium, and this condition of equaling the Fermi levels of two semiconductors leads to band bending at the interface, because on one side you have electrons in excess, on the other side you have holes in excess on the p side. As a result, electrons have a built-in concentration gradient from n to p side, and holes have a built-in concentration gradient from p to n side. However, at equilibrium diffusion current cannot drive once the junction is established, there is a opposing, because of band bending at the interface, there is opposing electric field which gives rise to drift current, which opposes the diffusion current, and these two diffusion and drift current balance out each other, leading to no current at equilibrium. However, because you have formed the junction, so the junction shows a region which is called as depletion region at the interface. So, this is for example the p and n, and this region at the interface is depletion region, in which there are no there are no free electrons, there are no holes in electrons. Basically what you have at the interface, this is the interface. So, if this is n side, you are going to have donor atoms here. So, these are donor atoms, positively charged, these are donor atoms, and on this side you are going to have the density of these atoms will depend upon and the width of this depletion region, as we will see, will depend upon how doped the semiconductor is. So, on this side you will have acceptor atoms, and holes and electrons would have neutralized each other. So, as a result, this region is called as depletion region. Depletion region, which means that it is depleted of any free charges, whereas in these regions, the regions where the bands are flat, so these regions are called as bulk regions. You still have excess carriers on both sides. So, this side will have lot of electrons, these are electrons, and and here you will have some holes, and on this side you will have lot of holes and few electrons. So, as we said earlier, that in this case Jn plus Jp total is equal to 0. Okay. Jn total is equal to Jn drift plus Jn diff, this is equal to 0, and Jp total is Jp drift plus Jp diff, this is also equal to 0. So, which means drift and diffusion currents are equal and opposite to each other for both holes and electrons. Any more migration of electrons and holes is not possible, because you have a built-in electric field, and this is called as VBI on both sides. So, this is called as VBI, and as we saw last time, this VBI was determined by equating the Fermi levels on both sides, and this VBI turns out to be kT by Q ln of Na Nd divided by Ni square. So, basically the built-in field increases as you it should be Na into Nd. built-in field increases as you increase the acceptor and dopant concentration in the semiconductors. This is what we did last time. Now what we will do is that we will look at some more aspects of p-n junction in a little bit more quantitative manner. For example, how wide is the depletion region? So first question is question number 1, how wide is this depletion region? That is the first question that we want to answer, and then we also know we also want to answer. So for this, what we take into consideration is, first we can make an approximation, which is depletion approximation. Okay. Now depletion approximation basically means is that you don't have any free carriers in the depletion region. By the way, if you want to do analysis of this, if you want to go into details of this, I would recommend you to go through the book. I'll write it here probably. I'll write it after this. Okay. So first is that there are no carriers in the depletion region. Second is in the regions away from the equilibrium, minority carrier determines from the junction, minority carrier determine the current, because majority carriers are nearly close to equilibrium all the time, because minority carriers get perturbed the most, and minority carriers move so a junction and depletion region. Here also it should be depletion region. Basically the region where electric field is equal to 0, where the bands are flat. So minority carriers move by the diffusion in regions away from depletion region, and where E is equal to 0. Since electric field is equal to 0, they can't move by diff, they can only move by diffusion. Okay. So which are called as in semiconductor in bulk regions. So the regions are called as bulk regions. Okay. So before I go into little bit more details of this, let me just mention the book. Books could be p-n junction diode by George, let me see what the name of the author is, George W. Nodek, and by S.M. Z. Then in the context of your solar cells, you can also look at physics of by Jenny Nelson. These are 3 books which can be useful to understand this whole p-n junction electrical characteristics in detail. So let me now go back to where we were. So first approximation is depletion approximation, which says that, as we saw in the previous slide, that there are no free carriers in the depletion region. In the regions away from the depletion region, minority carriers determine the current, and minority carrier move by diffusion in the regions away from depletion region, where electric field is equal to 0. Wherever you have flat electric field, flat energy bands, which means electric field is equal to 0, because you have to take the derivative of potential and since potential is related to energy, which is minus Vy minus E by Q, and from that you will determine zero electric field. So next approximation is called as superposition approximation. This basically means is that the recombination rates are basically Rn or Rp are linear in the neutral regions. Basically neutral regions are the ones which are where the electric field is 0. So neutral field is, you can say, is the bulk region. Okay, bulk region. There are multiple name, quasi neutral regions and bulk region and so on and so forth, and this is basically applies to minority carriers. Okay. Okay, so basically R of n is equal to R of p is equal to delta p by tau p. This will be in n type. Okay, and Rn would be equal to delta n by tau n. This would be in p type. All right, this we have seen. So they are basically linear. They go as a linear function of delta p and delta n. And if you have light present, if you have bias present, so you might have presence of light, some light may be present, and you might have applied potential. The effects produced by these two are decoupled. Okay, so effects of light, because light can change the carrier concentration, right? As a result, it can change the diffusion gradient, whereas bias can lower or lower the barrier at the interface. So effect of light and applied bias, that is external field, are independent or decoupled, to be more precise. Okay. So let us see the situation is so we define this we define this p-n junction as you know, if you have a p-n junction like this is the interface. Somewhere here we have the boundary of depletion region. Okay, so this, let us say, is x is equal to 0, which is the perfect, which is the junction, and we assume that this is a perfect interface. Okay, and we derive this as Wn. So this is p side, this is n side. So this is depletion region. Let us say here we have positive donor ions, right? On this side we have negative acceptor ions, but there are no free carriers. All right, so this is minus Wp, this is plus Xn, this is minus Xn. So this side is n type and this side is p type. Okay. So the basic, let us first look at the essential equations. So the essential equations is that we know that electric field is equal to minus of d phi by dx. All right. Now we have an equation which is called as Poisson's equation. Which basically tells us it applies in a region where you have a charge distribution. So for a region with charge distribution. All right. So this is, so if you have, let us say, d is the dielectric displacement, d, which is related to displacement. Okay. If d is the displacement, then divergence of d is equal to rho. Rho is the charge density. Okay, so or you can say del dot D is equal to rho, and from basic physics that we know that D is equal to epsilon S into E, where epsilon S is the dielectric constant of the semiconductor and E is the electric field. Alright. So, from this we can say that del dot E is equal to rho divided by epsilon S, or you can write del 2 phi is equal to rho divided by ES, sorry, epsilon S minus of. Okay. So, that is how you can write it as. So, now so basically Poisson's equation says that del of E or divergence of E is equal to rho divided by ES. Rho is the charge density, this is divided by, so divergence of electric field is basically proportional to the charge density in the material. This comes from the basic physics, right. So, now in the context of p-n junction, first we write for minus, for x being between minus Wp and 0. So, within this region we have the acceptor ions, right. So, del E by del x in this region is equal to minus of q n A divided by epsilon S, because we have negative charges in that region. So, rho will be minus of q into n A. n A is the acceptor ion density, whatever acceptor ions are there within that region, into q the electronic charge, and since they are minuses, we have, since they are negative charges, we have added a minus here, divided by epsilon S. For the region on n side, x between 0 and Wn, it would be del E upon del x being equal to q Nd divided by epsilon S, by the same analogy, right. On one side you have positive charges, on the other side you have negative charges. Now, if you look at the electric field on p side, so first look at the electric field. On p side. So, for p side we know, which means that it is we are talking of x minus of Wp. So, this is p side, this is on n side. So, for electric field we know that from the, we need to apply first condition, that is the boundary condition, E at minus xp is equal to 0, which means far ends of the semiconductor electric field is equal to 0, because the bands are flat, right. So, E at minus xp is equal to 0. So, we then write dE to be equal to minus of q n A divided by epsilon S into dx. Now, we need to integrate this. So, we integrate this from 0 to Ex, and this is integrated from minus of Wp to x. So, this is within the depletion region, right. So, when we do that, we have E as minus of, so this condition we know that electric field at minus xp is equal to 0, because at the end of the semiconductor the bands are flat, as a result there is no electric field there, but we are interested in calculating the electric field in this sense. So, in that sense it is not a boundary condition in that sense. So, it is minus of q n A divided by epsilon S integrate. So, if you do integrate, what you will get is x plus Wp. So, this is E is equal to minus q n A divided by epsilon S into x plus Wp, for x being between 0 and minus Wp. Okay. This is for the electric field on p side. Now, the same thing if you want to calculate for electric field on n side. So, when we look at the electric field on n side between x being from 0 to Wn, then first condition is that E electric field at Wn is equal to 0, because it is 0 at the boundaries of depletion region and the quasi-neutral region. So, Ex is now calculated by integrating the electric field from Ex, because electric field is continuous in the depletion region, and then it becomes 0. So, this is dE, and this is integrated from x to Wn, and this becomes Qnd divided by epsilon s into dx, and if you integrate it, you get Ex as minus of Qnd divided by epsilon s into Wn minus x. So, remember, it is integrated from Ex to 0, that is why this minus sign comes, and this is valid for x being between Wn to 0. So, this is how we calculate the electric field, and next we look at the potential across the depletion region from the edge of depletion region on P side to the edge of depletion region in the N side. So, we know that since d phi is equal to d phi by dx is equal to minus of Ex, again you can do this by integrating. So, I will not do that, but you will obtain for P side phi x as Qna divided by 2 epsilon s into x plus Wp square. So, this is less than equal to 0 minus Wp, and for the N side you will obtain phi x as minus of Qnd 2 epsilon s into Wn minus x square plus Vbi, okay, because let me just write the basic expressions, because for P side you will have d phi by dx as Qna divided by epsilon s into x plus Wp, whereas for N side this will be, you will have to integrate it from, so if you look at phi x, it will be integrated from, so basically the integration will take place from phi x to Vbi, because you are going from, so because you are starting like this, right. So, this is Vbi. So, the maximum value on the other side it takes is Vbi. So, this is for, so if you are starting from 0 on this side, it will achieve some value at the interface, and then maximum value it can take is Vbi. So, that is the maximum value. So, the integration will take place from phi x to Vbi, and Vbi we already know. So, basically the phi x would be this. So, this would be Vbi minus phi x. So, whatever phi x you will have, it will be Vbi minus of something, all right. So, now let us see what is the depletion region width. Now, since we are saying that at the interface the potential is continuous, what it means is that phi at 0 minus is equal to phi at 0 plus, all right. So, as a result, if you now since you have these two expressions, phi x for this is for, this would be Wn, okay, on this side. So, since we are saying that potential is continuous at the interface, so which means phi 0 minus is equal to phi 0 plus, and then when you apply this to previous equations, you get Qna divided by 2 epsilon s into Wp square, which is equal to minus of Qna divided by 2 epsilon s Wn square plus Vbi, okay. So, essentially you substitute x is equal to 0 in both the equations. So, you get this equality, and we know that we said that charge density distribution is like this. this is the interface, and on one side at the depletion region, on one side you have acceptor ions, on the other side you have donor ions, right. So, this is up to a width Wn, and this is Nd, right. This is Na and this is minus of Wp, all right. Okay. Since the solid is charge neutral, which means that on both sides of depletion region, Wp, because of charge and mass conservation, Wp Na should be equal to Wn Nd. The area of this rectangle is equal to area of this rectangle. It may be asymmetric, so one may be high, one may be low, but so you can see that if Na goes up, Wp will go down, if Nd goes up, Wn will go down. However, the charge density, the positive charge density on one side of depletion region is matched by the negative charge density on the other side of the region. So, otherwise you will not have electroneutral or junction will not be at the equilibrium. So, you can say that from this I can write down Wp is equal to Wn Nd divided by Na. So, if you now make the substitutions of this in the previous equation, you can calculate what is Wn. So, if you do that, you will find that Wn is equal to 1 over Nd into square root of 2 epsilon s Vbi divided by Q into 1 over Na plus 1 over Nd. And if you do the similar thing for Wp, you will obtain Wp as 1 over Na into square root of 2 epsilon s Vbi into Q into 1 over Na plus 1 over Nd. So, this is this is Wn and this is, so basically you got this equation, okay. You got this equation, you got this equation, you use these two equations to find out what is Wn and what is Wp, okay. In terms of donor concentration, acceptor concentration, Vbi and electric constant, okay. So, we have got two expressions for Wn and Wp. So, we know that capital W, which is the depletion region width. So, depletion region width W is equal to, what is it? Wn minus of minus Wp, all right. So, basically it is Wn plus. So, if you now sum them together, what you will obtain is square root of 2 epsilon s Vbi into Na plus Nd divided by Q Na Nd, or alternatively you can write this as 2 epsilon s Vbi divided by Q into 1 over Na plus 1 over Nd. This is the relation of charge density, or you can say acceptor and donor density, and the built in electric field with respect to the depletion region width. So, what it tells you is that when the donor and acceptor density increase, the W goes down. So, this is what we have done in this lecture. So, basically we have looked at some electrical parameters, the continuity of potential, electric field, the basic equations for electric field and potential. Remember that they are continuous in nature at the interfaces, and from this we can determine what is the so you can plot using those equations what is the electric field, what is the potential, and what is the charge density, and you can estimate what is the built in what is the depletion region width, okay. So, we will stop here in this lecture, and we will continue this in the next lecture to work out the electrical characteristics of p-n junction. Okay, thank you.